Welcome everybody. Today we are going to talk more about potential energy by looking at a block and spring system. In particular, I've set this up so that the origin is located at the same place as the equilibrium position of the spring. When I do that, the spring force has this friendly linear form equal to negative k times x. And what I'm going to do is I'm going to plug that into the expression we found previously for the change in potential energy due to a conservative force, which the spring force is an example of. When I do that, I'm just going to take this force, plug it right in over here. You can see the very first thing that happens is I get a dot product between the x vector and the dx vector, both of which point in the direction of increasing x, which means I'm going to get a positive result from my dot product. So what I have here is a negative sign from the definition of the change in potential energy, the integral of minus kx dx. And in physics, we almost always do definite integrals, so I'm going to put x initial and x final as my limits of integration. Like all integrals, anything that's constant here, like the -1 and the k, can be pulled outside of the integral. So this integral is not terribly difficult. X dx is going to go to x squared over 2. The minus signs cancel. So I end up with 1/2 kx squared as a result of the integral, which I need to evaluate from x initial to x final. Now in general, I plug those in. What I'll get very quickly is 1/2 kx final squared minus 1/2 kx initial squared. But it's also very common when you're dealing with potential energy to take a step back from change in potential energy and define just a potential energy function, which here would be the result of the indefinite integral, 1/2 kx squared, where we have to have it understood that we have chosen x equals 0 to be at the same location as the equilibrium position of the spring. And now I can always plug in an xi and an xf into this expression to get a change in potential energy.